In question number 22, the data states that we have a cyclist and the mass of the cyclist along with the cycle is given to be 100 kilograms. G is assumed to be 10 meters per second square according to the question. So that would mean that the weight of the cyclist along with the cycle is 1000 newtons. Further, the speed of the cyclist, let's call it V, is mentioned to be uniform. The cyclist is traveling at a uniform speed, and that has been given to be 18 kilometers per hour. And when you translate it into meters per second, this uniform speed turns out to be 5 meters per second. The track along which the cyclist is moving consists of two parts. The first part is ABC, and that forms a quarter circle. So ABC is this is point A, point B is over here at the top, C is over here. So since this subtends an angle of 90 degrees at the center of the circular arc ABC, clearly this is a quarter circle. The second part of the track is another quarter circle, CDE. So it starts at C, it starts going down like this, and then it goes up like this. So this is point D at the bottom, E is over here. And once again, if I draw these two perpendiculars or radii respectively at C and at E, then at the center of this circular arc they subtend an angle of 90 degrees. So once again, the second part of the track is also a quarter circle. Now the radius of each quarter circle, R, is the same, and that has been given. So this is R, this is also R, and R has been given to be 100 meters. So I'll just write it down over here in the data. The radius of each quarter circle is 100 meters. Now there is one way that we have to interpret the question. If you read the further sub questions, if you read all of them, then you realize that the question talks about the cyclist being at point B, or the cyclist being at point C, or at point D, and so on. A moment's thought will convince you that because the cyclist along with the cycle is a large body, that is, it's not a point, it's not a particle, there is no way that the cyclist can actually be at point B. The other problem of finding meaning in this particular statement that the cyclist is at B, etc., is that maybe the questioner is talking about the point of contact of the cyclist with the track to be at point B. But once again, the problem is there are 2 points of contact, one for the back wheel and one for the front wheel. So obviously this is not the meaning which is intended in the question. So the only thing that I can think of is the following. The easiest way for us to interpret the statement that the cyclist along with the cycle is at a point B or C or D is to assume that the dimensions of the cyclist along with the cycle, the dimensions of the cycle as well as the cyclist, are much smaller than the total length of the road. Now that would automatically mean that these dimensions are much smaller than the radius R of each quarter circle. So what I am effectively saying is we are free to assume that the cyclist along with the cycle is approximately a particle which is moving along this particular circular track like this. Circular meaning composed of 2 quarter circles. So you assume that the cyclist is a particle, and then this makes sense. The particle can be at B, at C, at D, and so on. So let's try part A. Question A asks us to find what is the normal contact force by the rod on the cycle when it is at B and further when it is at D. So let's investigate what happens at point B. So let's draw the free body diagram of the cyclist plus cycle when it is at point B. Remember, we are assuming that the dimensions are very small, so I'm just going to represent the body by a dot. It's like a particle. Now what are the forces acting on this cyclist plus cycle? At point B, the weight is not going to change, it's mg in the downward direction, and that we have calculated to be 1000 newtons. Likewise, the other force acting on the system is the normal reaction, which we want to find. So we call it NB. It's the normal reaction exerted by the rod on the cycle. Now there could be friction, we are not sure, and the friction we'll assume it's going to be static friction by assuming that the tires are not skidding on the ground. So if it's present, it's going to be static friction, and it has to be, if present, in the tangential direction. Could be forwards or backwards, but I'm not sure whether this force is positive or negative, so I can draw it like that. It could be 0 in fact. So this is the general FBD. Now of course the next thing in the FBD is to draw the acceleration of the cyclist. Now the acceleration has two components in general in circular motion. One of them would be the tangential component. Now the tangential component of the acceleration, AT, when the cyclist is at B, it must be 0 because the speed of the cyclist is not changing, and the tangential acceleration is nothing but the rate of change of speed. In fact, this particular argument can be applied wherever the cyclist is on the circular path, because if the cyclist is here or here or here, it has been given that the cyclist is moving at a constant speed, at a uniform speed, which means the rate of change of the speed is always going to be equal to 0. So the tangential acceleration at any point of the path must necessarily be equal to 0. Of course, the second component of the acceleration of the cyclist plus cycle when at point B is the normal acceleration, which is also called the centripetal acceleration because it is towards the center of the circle, namely towards this point. And the value of that normal acceleration, the symbol is AN, of course, the value is V square divided by R. Now if you calculate V square upon R, let's see, I'll put it over here so that I can use it later on also. A normal is V square upon R, but V is given to be 5 meters per second. So 5 square upon R. So what is R? 100 meters. So this turns out to be 1/4 meters per second square. So at point B, if I apply to the system Newton's second law in the normal direction, what I get is mg minus nb equals mv square divided by r, and I can now substitute mg is 1000 minus nb, I want to find it, is m is 100 kilograms into v square upon r is 1/4. So this turns out to be 25 newtons, and my answer for NB turns out to be 1000 minus 25, which is of course 975 newtons. Now this number I may require later on in the question, so I'm going to put it in the figure in the proper place. So I will rub out some unwanted things. The AN being equal to v square upon r, I'll just rub it out. AT equal to 0, I'll rub it out. I think I'll allow the forces to remain, and just below NB I'm going to write 975 newtons. The value of NB is this much. Likewise, I want to find now what is the normal reaction when the cycle is at point D. So I'll show a particle at point D, and of course I have to draw the FBD. The weight of the cycle is still 1000 newtons, mg is 1000 newtons. The normal reaction exerted by the road is a push, like that, so that's Nd, and if at all frictional force is present, it's going to be static friction because of no skidding, the assumption, and also it will be tangential, so I'll assume it's backwards. We'll calculate it later on in another part of the question. Fs, and since it is at point D, I'll just add the letter D here. Likewise, the first frictional force, which is shown at point B, I'll just change the name to FSP. Now the accelerations. The tangential acceleration is equal to 0, we know that, and the normal acceleration is now in the upward direction. The center of the circle has changed now, it is this point, so that's the direction of the normal acceleration. The normal acceleration is going to be directed towards that point. Now that's an, it's v square upon r, but remember v and r are still the same as before, so v is 5 meters per second and r is 100 meters, so I still get my old value of 1/4 meters per second square. The normal acceleration's magnitude is still 1/4 meters per second square. So when I apply Newton's second law, sigma f is equal to ma in the normal direction, that is in the upward direction at point D, what do I get? I get Nd minus mg equals m times v square divided by r. Now I substitute Nd, want to find it, minus mg is 1000 newtons, is mv square upon r is 100 into 1/4. Now that's 25 newtons. So Nd, the normal reaction when the cycle is at point D, is 1000 plus and not minus as before, so 1000 plus 25 newtons, and that of course is 1025 newtons. The normal reaction at point D is larger than that at point B, and one other way to visualize why the normal reaction is larger is to take a rotating reference frame. So when the cycle is at point B, the rotating reference frame should be centered at this point, and it should be rotating along with the motion of the cycle. In that case, the centrifugal force in the rotating reference frame would tend to throw the cycle off the road, and that would reduce the normal reaction. Whereas in the second part of the motion, when the cycle is at point D, the rotating reference frame is centered at this point, and in this reference frame, once again the centrifugal force is in the radially outward direction, like that, but this time the centrifugal force presses the cycle against the track, and thereby it increases the normal reaction. That's why the normal reaction at D is larger than the normal reaction at point B. Right, so this 1025 newtons, which is the normal reaction at point D, I'm going to put it in the figure after rubbing out some unwanted things over here. So all this I rub out, and for our reference we are now going to write what is the normal reaction. It is 1025 newtons, that's Nt. Now we have to turn our attention to sub question B, in which we want to find what is the frictional force on the cycle at points B and C and D. So let's first begin by finding the frictional force at point B. Now at point B, we have already noted that the tangential acceleration, which I'm drawing right now, the tangential component of the acceleration is equal to 0 because the cycle is moving at a uniform speed. So I will now apply Newton's second law, F is equal to ma, in the tangential direction to the cycle plus cyclist. Clearly, since the acceleration in the tangential direction is equal to 0, sigma f in the tangential direction must equal 0. If you look at the figure, you will see that the only force acting in the tangential direction seems to be the static frictional force Fsb. Clearly, this force must be equal to 0, and that means that the frictional force on the cycle at point B is equal to 0. Now, let us likewise find the frictional force on the cycle when it is at point D. Now, just like at point B, the tangential acceleration of the cycle at point D is also equal to 0. Clearly, when I apply sigma f is equal to ma in the tangential direction at point D, once again the total tangential force is equal to 0, and that implies that the frictional force, the static frictional force it is, on the cycle at point D must necessarily be equal to 0, and this is of course at point D. I have changed the order of the points because point B and point D you get a similar result. Now let us turn our attention to the cycle plus cyclist when it is at point C, which is the next point, the remaining point given in the question. The forces acting on the system at this point are once again mg, which is 1000 Newton acting in the downward direction, and there will be the normal reaction at point C, I'll call it NC, and there could be a static frictional force tangential to the path, which I'll call F static, Fs, and C. And once again, because the speed of the cyclist doesn't change with respect to time, the tangential acceleration at is going to be equal to 0 at point C. Now, to make the picture a bit clear, I think I'll move this force mg to this position. It will look a bit clearer. This is mg, which is 1000 newtons, and this angle, by geometry, we can easily prove it to be 45 degrees. Since the diagram has become slightly cluttered up, I'll remove certain unwanted things. For example, at point D, the frictional force has been proved to be equal to 0, so we can remove this. Likewise, at point B2, the frictional force is equal to 0, so we can remove these arrows. Yeah. Now, this is point C. We now apply sigma f tangential is equal to mass times tangential acceleration at point C, and we know that the tangential acceleration is equal to 0, so basically sigma f tangential is equal to 0. Now, unlike at point B and at point D, there is another force in the tangential direction which has a component in the tangential direction, that is apart from the frictional force, and that is mg. So this equation is going to be a bit different from my previous equation. It's going to be mg times cos 45 degrees minus the frictional force at point C is equal to 0. Of course, we substitute mg as 1000 newtons and cos 45 as 1 upon root 2. So what you get is the static frictional force at point C on the cycle must be equal to 1000 newtons divided by root 2, and that's approximately 707 newtons. And of course the direction of this frictional force is parallel to the track, like that, and this angle is 45 degrees. So it means that when the cyclist is at point C, the frictional force is non-zero. It is 707 newtons up the track. Now there is one point over here which I would like to make, which is going to be useful in another part, another sub-question of this same problem. It's going to be useful in the last part, part D. If I ask what is the frictional force on the cycle at a point just before C or at a point just after C, I think one realizes that what is being asked is the frictional force on the cycle just around C, in this region. Now it is going to be approximately equal to 707 newtons itself, and the reason is around that point, whether it is slightly before C or after C, the tangential force on the cycle is still equal to 0 because the tangential acceleration is 0, and the equation sigma f is equal to 0 will yield mg multiplied by, now it's not going to be cos 45 degrees, it may be a bit different, slightly different than 45 degrees, because I'm going slightly up or down from C. We are talking about a point which is slightly before C or slightly after C, so roughly 45 degrees, very very close to 45 degrees, and minus f static is equal to 0. F static is equal to 0. It's not point C, of course, it's slightly before C or after C, so maybe the C I can rub out. Now clearly the static frictional force slightly before or after C is once again going to be very nearly 1000 upon root 2, because the angle is very close to 45 degrees, and so 707 newtons, this particular figure, it can be taken to be the static frictional force on the cycle around point C, not only at point C but also around point C. This point is to be made note of. As I said, it is going to be useful in solving part D, the last part of the question. Now let's go to part C. In this part we have to find the normal reaction acting on the cycle just before point C and just after point C is reached. So we'll require a slightly bigger diagram. Maybe I can move this up like that, and let me try and draw an enlarged diagram as to what is happening around point C. So that's the diagram, and point C has been shown. Now let's consider a point which is slightly before point C. That is, the cycle reaches this point just before it reaches C. Maybe it's somewhere over here. I want to give it a name, so I'll give it the name C minus. C minus would mean before C, just before C. And likewise there is another point which is somewhere over here, and since it is reached just after C, I'll give it a name. I'll call it C plus. Right. So the question which we are doing, the sub question, is part C, and we want to find what is the normal reaction on the cycle at these 2 points, just before and just after point C. So initially we'll try to find what is NC minus. So to do that, I will draw the FBD of the cycle, assuming once again that it is a particle for the reason stated before, and the cycle is assumed to be at the point C minus, like that. Now let's see what are the forces. One of the forces is of course mg in the downward direction, that's 1000 newtons. Okay, the other forces acting on the cycle, one of them is the normal reaction, which is what we want to find, of course, so that's Nc minus. And lastly, there is static frictional force, which is tangential and in the upward direction, the tangentially upward direction, I'll say. And this we have calculated in the last part of the previous sub question to be 707 newtons. Remember, 707 newtons was actually at point C, but at the very end of the discussion we stated that the static friction would be very nearly 707 newtons at point C minus as well as at C plus. So this force is the force of static friction, 707 newtons. Now this angle is clearly 45 degrees. We are talking about a point which is very close to C, remember. So the angle is very nearly 45 degrees, I could say that. Yes, now we have to find the, or we have to draw the centripetal acceleration in the figure. But for that we must know where is the center of the circular path. Currently the cycle is just before C, so there is no doubt that it is moving on this circle, and therefore the center is over here. The centripetal acceleration, the normal acceleration, will hence be towards that point. So I will now show it in the FBD as follows. The centripetal acceleration at point C minus is in that direction, A normal that is, and that's of course v square upon r, and that we have already calculated in the previous parts to be 1/4 meter per second square. And I'll now apply F is equal to ma to the cycle plus cyclist in this particular direction, in the centripetal or in the normal direction. So what do I get? I get the component of mg in the centripetal direction is 1000 cos 45 degrees minus nc minus, because nc minus is in the radially outward direction, it's against the centripetal acceleration, that's equal to mass times acceleration. So mass is 100 kilograms and the centripetal acceleration is 1/4 meter per second square. Now that's 25 newtons. So what I get is nc minus is 1000 cos 45 degrees, so that's 707 newtons minus 25, and this turns out to be 682 newtons. Now let's do a similar procedure when the cyclist is at point C plus. So the cyclist is over here. What are the forces acting on the cyclist? So one of them is of course mg, so mg, that's 1000 newtons. The second force acting is the normal reaction, this one over here. So we have to give it a name. I think what I'll do is I'll move the normal reaction over here so that you can make it out properly in the figure, and the name is NC plus, either about this, okay, and the frictional force is up the track like that, tangential, it's static frictional force, and as discussed earlier it is very nearly 707 newtons. Now the cyclist is moving on a completely different circle when it is at C+. It's moving on this circle, and so the normal acceleration or the centripetal acceleration must be directed towards the center of that quarter circular arc. So it must be directed towards this point. So I'll show it in the FBD. The normal acceleration is in that direction, A normal. That's v square upon r, and already calculated to be 1/4 meter per second square. Now let's apply Newton's second law of motion in this particular direction, in the normal direction. So what do I get? I get at, well, I want to find NC plus, that's the question, and I get NC plus this force minus mg cos 45 degrees. Remember, I'm talking about this particular force mg and the component in this direction. Now this angle is very nearly 45 degrees, so that explains mg cos 45 degrees equals mass times acceleration. So mass times v square upon r, substitute nc plus minus 1000 newtons times cos 45 degrees equals 100 kg into 1/4 meter per second square, that's 25. So what I get is nc plus, the normal reaction of the track on the cycle at point C plus is 1000 upon cos 45 degrees is roughly 707 plus 25, and this of course is 732 newtons. Now we turn our attention to part D, in which we want to find what is the minimum value of the friction coefficient between the road and the tire, which will ensure that the cyclist can move with constant speed. Now to do this problem, we will first show that point C minus is the place where the cyclist is most likely to slip. And the reason for that? The reason is at C minus we will prove that the normal reaction exerted by the track on the cyclist is minimum. Now that would automatically mean that mu times normal reaction is minimum, which would also automatically mean that the maximum value of friction which the track can exert on the cycle is minimum at point C minus, and we will also show that at C minus the requirement of the static frictional force is maximum. So if you look at it, you realize you need something you need the most friction at point C minus, but the amount of friction that the road can supply at point C minus is minimum. So a moment's thought will convince you that it is point C minus where slipping, if at all it occurs, it is the place where slipping is most likely to occur. So our approach in solving part D will be to ensure that slipping doesn't take place at point C minus. In fact, we will assume that at point C minus the cyclist or the cycle rather is just on the verge of slipping. So we'll assume the limiting friction case at point C minus, and if that is the case, then slipping will not take place anywhere on the track. So let's first prove that the normal reaction of the track is minimum at point C minus. Let me move this up. Now if the cyclist is somewhere over here in the first quarter circle, then he's traveling along this circular arc whose center is over here, and this angle is an acute angle theta. And if I draw the FBD of the cyclist, I have mg in the downward direction, this angle is theta, and I have normal reaction N1 in that direction, and there may be some frictional force which is Fs. Also, the acceleration of the cycle is in this direction, and it is given by v square divided by r. Now when I apply Newton's second law in the normal direction, what do I get? I get mg cos theta minus n1 is equal to mv square divided by r. So I get n1 is equal to mg cos theta minus mv square upon r, and we want to find the place where n1 is minimum. We want to minimize n1, so clearly that's going to happen when cos theta is minimum. So that will happen, noting that theta is an acute angle, it will happen when theta is max, and that maximum value of theta, remember, the cyclist or the cycle should still be on the first quarter circle. So the value of theta, that is the maximum value of theta, will correspond to the cyclist just being on the edge or almost on the edge of the first quarter circle. So we are talking about theta max being very nearly 45 degrees. On the other hand, when the cyclist is at an arbitrary point on the second quarter circle, then the FBD is going to look like this. This is mg in this direction, and the normal reaction, I'll call it N2, is in this direction, and if I draw the radius of that particular quarter circle, the center is maybe somewhere over here. Now let's assume that this angle is theta, and the acceleration in the normal direction is v square upon r. So once again I apply Newton's second law of motion in the centripetal direction, but now I am on the second, the cyclist is on the second quarter circle. So what I get is N2 minus, now this angle is the same theta, minus mg cos theta is equal to mv square divided by r. So I get N2 is equal to mg cos theta plus mv square divided by r, and because theta is now decreasing, it's an acute angle which is decreasing from roughly 45 degrees to 0, and then even smaller than 0, it will become negative when the cyclist goes past the lowest point D of the second quarter circle. Now we can see, after a bit of thought, that the minimum value of N2 is going to occur when cos theta is minimum, and that's going to occur at point C plus, just after C has been passed. So when we want to look for the place where the normal reaction is minimum, it's going to be either C minus, which is the place where normal reaction is minimum on the first quarter circle, or on the second quarter circle it's C plus. It's either C minus or C plus. But if you remember, we have already proved that the normal reaction at C minus is 682 newtons, and at C plus it is 732 newtons. Now that indicates that at C minus you have the least normal reaction on the entire journey on the track. Secondly, as the cyclist travels down along the track, rather, the place where the inclination of the road is the most is around C, and that is the place where, if the cyclist wants to continue traveling at the same uniform speed as before, the frictional force must be maximum because the inclination is maximum. So that indicates that around C the required static frictional force is maximum. So as explained earlier, well, around C would include C minus, and as explained earlier, C minus seems to be a critical point where you require most friction and you can get least friction because the normal reaction is minimum. So at C minus, let me remind you that at C and around C the required frictional force is roughly the same whether you are just before C or after C or on C, and that's over here 707 newtons. So the required friction is 707 newtons at C minus, and the normal reaction at C minus, it's already proved that it's 682 newtons. So if the cyclist is just on the verge of slipping at point C minus, then we can write the frictional force required is 707 newtons, and that's equal to mu multiplied by the normal reaction at that point is 682 newtons, and what you get is the critical value of mu. It's 1.037. Now this value of mu, or any value of mu greater than this, would ensure that the cyclist doesn't slip at any point whatsoever on the path. Now students will no doubt observe that the question actually asked us the minimum value of mu so that the cyclist can move with a constant speed, and we found the minimum value of mu so that the cyclist doesn't slip. So constant speed was the condition given in the question, and we converted it into the cyclist not slipping anywhere. So this is left as an exercise to the students why these two conditions will correspond to each other.